So next we're going to look at some data visualizations, and we're not going to look at really serious ones. So later on we'll play with some better visualizations, but we're just going to work with the basic ones that come as SPSS outputs or as other Excel will do this, other stats programs will do this, but just some of the basic ones. So one of the things you need to know is that data visualization is always important. And no matter, and there's some programs that do this much better than the program that we're going to use primarily. So ArcGIS does a great job with data visualization, not just with maps, but with ArcGIS Insights, which is a program. Power BI does a lot of data visualizations. Tableau does a lot of data visualizations. So I want to make sure that you know that this is important. But this is not always the case. And again, it's my rap against mathematicians, except for a couple. And so one of my heroes is a guy by the name of John Tukey. And John Tukey was a statistician in the mid-20th century. And what he said was this. He said, we got all these numbers and they're really good, but if we're going to have people understand these things, we need to figure out how to visualize it in a way that makes some sense. And one of the things that Tukey did, he created some very simple basic visualizations, some of which we're going to use in this class. But what he did was he really transformed the mindset of a group of analysts who said, yeah, you know what? We need to think about how we visualize data, how we actually represent it in pictures. And so this is going to be another piece that we're going to work on during the term. But when Tukey was working, computers were not very good, and so he did most of his by hand. But one of the things is that computers do these things easily and quickly for us. And so something like a histogram, which, by the way, when I was even a graduate student, I had to actually hand draw my histograms. The computer programs really were not very good at doing this automatically. But one of the nice things is that you can actually generate a histogram online, and actually I've used an online program here, but SPSS will do that for you consistently. And all a histogram does is this, is it says, okay, how many times does this particular data value or this range of data values occur in the data set? That's all it does. And what it does is it creates a picture of the data. Now the question is this data normally distributed or is it skewed? And in your head, some of you are thinking, it's normally distributed. It looks kind of normal to me. Others of you are going to look at it and say, I think there's a skew there. And the question, and the thing is that for mathematicians, there's always a normal data set, right? And this is this perfect imaginary thing. Those of us who work in the professional world, we really have a sense that if we run across a normal data set, something must be horribly, horribly wrong, because none of them are normal. But many of them are near normal. And so what we need to be able to kind of distinguish is not whether it's normal or not, but whether it approximates a normal curve. And so we'll talk about what that means. And histograms help us do that. This is what a normal curve looks like. You've seen these before. It's often called a bell curve because it's shaped like a bell. I like the term Gaussian because that's the person who originally devised it. One of the things I often tell students is that it provides us with some magical properties, and I tone that down a little bit now because I had students who were just taking that phrase and using it on exams and things like that in ways that it should never have meant. But one of the things you can do with a normal distribution is you can do some extra things with your data that you can't do with a skewed distribution. And we'll talk about that in some of our analyses. Your distribution can be shaped a variety of ways. And so even if it's normal, there's only usually one mode or one peak. Sometimes you have a bimodal distribution where you have two peaks or multimodal. You can have a variety of shapes of data sets. Sometimes data misbehaves all the time, and so you need to kind of think about that. Sometimes your data sets are skewed, sometimes they're right skewed, sometimes they're left skewed. This happens a lot. This happens particularly in income data. If you ever deal with income in any of your data sets, I will bet you every time that it's right skewed. I will bet you every time that you are dealing with skewed data and it's right skewed. Most of the population has fairly low income. High incomes are fairly infrequent, and it's definitely right skewed. And if you don't believe me, go look at some income data. When you group your histograms, you want to group them into intervals that make some sense. You want somewhere between 5 to 10 intervals in your histogram. And you can think about the size of your interval width. And one of the things is that that's probably a nice histogram. It's got more than 5, but it gives you the shape of the data. You want to give the shape of the data without going into too much detail in that. Sometimes we deal with the cumulative frequency, and we do this in an upward graph, looking at how much of the percentage of the total frequency do we have at different data points. We don't use this that often, but sometimes this is appropriate to use in some reports. SPSS will put this out for you. I just don't like stem and leaf plots. I think they're ugly, and I think that a histogram will do me just as well. Some people are in love with them. This is actually how Tukey actually did his work. So as much as I love Tukey, I hate his stem and leaf plots. But basically, you take your stem, which is the first digit of a 2-digit number, and the leaf, which is the second digit, and you begin to kind of plot it out. And so for that last column, you have 63 and 66. That last row, you have 63 and 66. The one above it, 52, 56, 57, 57, 58. You can kind of see how it works. SPSS will do these for you pretty easily. SPS will also do these for you as well, box and whisker plots. And the box is the interquartile range, and then the whisker is the quarter plus 1.5 of the quarter, and then it will show the outliers. And so it's a really nice way to kind of show where the major portion of the data set is, and SPSS will do that for you as well. But your distributions don't always have the same shape either, and so we want to talk about that. And so these pieces here, back here, we go here, we talk about skew, and we can actually measure the skew. But here we go. Here, it's not skew. These are all symmetrical curves. What we're measuring is the kurtosis, or the peakedness of the data. And so one of the things I want you to think about is that your data sets will differ in how they spread, right? So it might be skewed to one way or the other, but it also might be narrow and peaky, or it might be flat and long, and you can measure that, and you can talk about whether or not your data set is like that. And so if you think about skew, a symmetrical curve has a skew of 0. Positive skew is right skewed, and the tail is off to the right, and it's great, and the skew value is greater than 0. Negative skew is skewed to the left, and it has a negative value. And what we don't worry about is we don't worry about small deviations. Now, the mathematicians will worry about this. We won't. If your skew is less than 0.5, plus or minus from 0, you can call it near normal and work with it as a normal data set. Is it a normal data set? No, but for all intents and purposes in the professional world, we can use it like that. Just some examples of skew and what it might look like. Now, kurtosis talks about the peakedness of the data. And I've given you the names leptokurtic and platykurtic. I'm fine with you just saying peaky and non-peaky. So know that if it's near normal, your kurtosis will be 3. If it's peaky and slender, it's going to be above 3. And if it's flat and broad, it's going to be less than 3. And those would be the measurements that you would look at. So, time to be brilliant. And so this is the theorem, and I had a student who agonized over this theorem this past year, and kept trying every time I talked about this particular piece, tried to actually like work the theorem. That's not what this is about. So the theorem is done. Chebyshev talks about how data for every data distribution lies around the curve, right? And so that's the theorem. That's what it looks like. 1 minus 1 over k squared. And you would calculate that. Where k is the number of standard deviations. So here's what I'm going to show you and I'm going to talk to you about is something that when I'm sitting in a boardroom talking, I'll do it on my napkin. So this is what Chebyshev's theorem says. And that's kind of the mathematician's piece. But in English, what that means is that for every data set you ever have in the rest of your life on the planet, is that 75% of the data lies within 2 standard deviations of the mean. Which means this. If someone's up talking and doesn't know what they're doing and just kind of lists off the standard deviations and the mean and things like that, what you do is you sit on a napkin and you actually figure this out, and we'll do this in the 4th video. Okay. Then 75% of our customers are doing this. And that's, and you can begin to kind of look brilliant on that. If you want to figure out the 3rd standard deviation, you can say, oh, well, okay, so almost 90% of our customers are doing this. Dollars to donuts, the speaker doesn't know that. Dollars to donuts, no one at the board table knows that. But if you know how to do this, and you can actually do this pretty easily. This is how it works. So, I have a mean of 28, I have a standard deviation of 3. I add 2 standard deviations to 28, I get 34. I subtract 2 standard deviations from 28, I get 22. I know that 75% of my data is between those 2 values. That's how it works. So this works for every data set. But what if your data set is actually normal, right? Or close to being normal? And this is what I mean by magical properties, is that you can talk about your data set even more. And so I remember in grad school I took stats, and guy spent an hour deriving the central limit theorem. And he was kind of like, the professor on Back to the Future, and he derived the whole thing, and then at the end of the hour, he just, now that is a beautiful statistic. It is. It really is. He did a great job. But here's what you need to know. Much like Chebyshev's theorem, where you can kind of say between 2 standard deviations lies 75% of the data, with the empirical rule and the central limit theorem, you know that 95% of the data lies within 2 standard deviations. If your data is normal, right? So if your data is not normal, you use Chebyshev's theorem. That works for every data set, including these. But if you know your data set's normal, you actually can kind of say, 95% of our customers are doing this. And that carries some meaning. You can begin to kind of use this to your advantage. All right. I have this here so you can play with this later. You can create different distributions. It's always fun. One of the things that I need to talk to you about is taking care of your data and thinking about outliers. And so going back to the Michael Jordan problem, it is perfectly appropriate to take Michael Jordan out of that data set. In fact, it's probably more honest. And so one of the things you need to think about is how you're going to eliminate data from your data set and do it ethically. So the first thing I will tell you is if you do filter data out of your data set, you need to tell someone that you've done that. So in your write-up, you need to say, we filtered out Michael Jordan because da-da-da-da. We filtered out 5% off the top and the bottom because of outliers. Perfectly legitimate. You just have to say that you did it. If you do it and then don't tell anyone, that's an ethical problem. And that's the kind of thing that gets you into real trouble. And sometimes you just get weird data, and so a data you might have measurement error of different kinds. So, for instance, I have a data set that is of Southeast Wisconsin houses, and when you map it out, I have houses in Tennessee and I have houses in Iowa and things like that. Well, someone entered the data wrong, and a lot of times, if you have real clinker data, you can throw it out. It's fine. It's not a big deal. This, however, is a big deal. And so I want to talk about Simpson's paradox, and I want to talk about modifiable area unit problems because they're both important. So we'll talk about Simpson's paradox first. So a university was accused of discrimination based on these numbers. And so if you look at it, we're admitting more men than women, right? These numbers look really bad. These numbers look really bad. And so lawsuit was brought forward. However, universities and most businesses work on a department level. And so when you begin to break it down into a department level, you get some different results. And whereas you can talk about whether or not, these results are equitable or not, we can have that discussion. What happened with the point of this example is this. When you change the level of analysis, you change the results. Now, what I just said sounds horrible, and I get that. When you change the level of analysis, you change the results, right? And that sounds like you're cooking the books. You can use it to cook the books. I'll grant you that. But I don't care. You can be the most honest, ethical analyst. If you change the level of analysis, you change the results. And so one of the things to think about is at what level am I going to do my analysis at? And one of the things I'm going to push you all on, and I'm going to be a real pain in the neck. Note, Julio, pain in the neck. I don't want to see projects done at the state level. I do not want to see projects done at the county level unless that's the smallest level of analysis that you can use. So I'm always going to push you to smaller levels of analysis. Things at the census tract and census block group level, individuals. When you create big groups, you can create obfuscations. And so one of the ways to deal with Simpson's paradox is to do your analysis at small levels of analysis. We'll talk about that more over the term, but I want to make sure that you know that if you change the level of analysis, you change the results. Same thing is true if you do it on a map, and we're not focused on maps particularly in this class, but the analysis will still hold if you do this at different levels. So if I change the level of geography that I'm working at, I change the results. And so I can work at this level of geography, I can work at the state level. And then, I think I have this rolling. What happens is I can change to a smaller level of geography, change the results. Again, I'm going to change to a smaller level of geography. Somewhere in my video here I do that. Evidently I don't do that, but you get the sense is that I've changed the results by changing the level of analysis. When we think about visualization, one of the great examples of visualization is Jon Snow. And if you don't know the story of Jon Snow was a physician during the cholera outbreak in London in the 1800s. And he had a hypothesis that, people are getting sick because of the water. And he got this hypothesis because he simply drew out the cases and where they existed on the map. And he convinced the local authorities to shut down the Broad Street pump. And they did that, and the cholera outbreak was taken care of. And so one of the things I want you to think about is, visualization of data makes sense because what happens is that you can begin to kind of tell a story in a different way. Now, whether it's mapping, whether it's graphing, no matter what you're using, I think you can begin to kind of think about different ways to visualize data. And we'll do some of that this term, but we're going to focus primarily on the stats. One of the things I want you to think about is that you're not about lying with statistics. You are about trying to represent the truth, and there's a lot of gray area in this. And so one of the things I'm going to ask you to do is look at the gray areas. Statistics is not about exact numbers. As I said in the other video, your data is fraught with error. You are trying to approximate what you think is happening, but it's not absolutely precise. With that, we're going to move to the fourth video on how to tell the story of the data.